The kilogram's gone. No problem. We will tell you why. In the 18th and 19th centuries, people in different countries used various different measurement units for their daily measurements. This became a problem, especially when trading goods across borders. Scientists became aware of that and defined two global measurement units, the meter and the kilogram. They made physical realizations of these units. A meter rod called the international prototype of the meter and a kilogram piece called the international prototype of the kilogram. They founded a laboratory, the BIPM, Bureau International de Poids et Mesures, in order to take care of these references. They manufactured national prototype pieces, copies of the international ones. Those should serve in the countries as national measurement references. In the late 20th century, two problems of this system became obvious. First, the national prototypes had to be brought regularly all the way to Paris for recalibration. Second, and more important, the system, especially in the case of the kilogram pieces, showed instabilities and drift.
The SI, International System of Units, was first created in 1960 by the 11th General Conference of Weights and Measures. And at that time, the president of the CIPM in those days said that there's one problem with the international system, and that's the kilogram, because it's still based on an artifact. It's an object that was made, manufactured, and the fact that it's survived all this time since 1889, this was 1960, is a minor miracle. So, you know, that's not a good way to do business.
As you now understand, this definition, as straightforward and easy as it sounds, is not perfect, since it relies on the stability of one single man-made artifact, the international prototype of the kilogram. So the idea was to find a defining constant of nature, an invariant natural constant, to define the kilogram.
Every community had its idea how to redefine the kilogram, and the mass community was no different. And so the final decision to redefine the kilogram based on a fixed value for the Planck constant that creates a quantum SI, so-called, because the Planck constant is the fundamental constant of quantum physics. Lots of people wanted that, but it took a while for mass people to accept that because it's such an abstract definition.
Already more than 10 years ago, we were asked the question, is it the right time to start? And it was, of course, too early because we didn't have enough material, enough experiments working at sufficient accuracy, and we decided to wait a little bit. But finally, we had to fix a deadline where we have to have all the available results in order to start redefinition. And this deadline was fixed in the middle of 2017, if I remember well. And since this deadline, all the experiments have to publish their best results, which were connected, which have the most recent traceability to the international prototype of the kilogram. And then we had a long process of decision. And finally, last November in Versailles, the General Conference approved the revision of the new international system of units.
Everybody was caught up in the moment, you know, that I think everybody felt that it was all that hard work over the years had finally been recognized and had borne fruit. And yeah, everybody, you could tell everybody in the room was energized. And
thank you. Now we I will initiate the vote, and we will go as follows. Each country will be called, and you will say yes or no.
Finally, I was at the General Conference at the head of the Swiss delegation, and was sitting in the front presenting the results of the CCM report, and then finally voting for Switzerland. Yes to the redefinition.
I hope that such votes will also be possible for many other issues for the world. So thank you so much.
I've always thought that the most remarkable achievement was the convergence of results between the people who are measuring the Planck constant in those days. You measured it in those days as a prerequisite, using two radically different techniques. One based on something called the Kibble balance, as electromagnetic force, and one based on a sphere of silicon, where you know the number of atoms of silicon in the sphere, and you can relate the mass of an atom to the Planck constant, which had already been done before they even started the experiment. So the fact that those two gave the same result, I found to be incredible. But not incredible, but very satisfying. So, and I think it really shows that physics works and that these people are very talented in the laboratory.
So welcome to NIST. We are here in the Advanced Measurement Laboratory, about 13 meters underground. And the instrument next to me is the NIST Kibble balance. And the NIST Kibble balance makes a connection between a constant out of quantum mechanics, it's called Planck's constant, to mass. So with this machine, we can basically use a fixed value of the Planck's constant to measure mass. And the way it is done is we have here a piece of mass that gets put on this balance, and we have here an electromagnetic compensation system that provides a force that is equal to the weight of the mass. And that force can be traced back to electrical units, which can be precisely measured with quantum electrical standards based on Planck's constant. So we use the wheel to move the coil up and down. So the wheel is like a balance beam, but because it's round, the coil moves perfectly vertical. It's like a pulley. There's no sideways motion that you would have on a beam. So this is what we call the rotation control. So we apply a voltage and we can pull the gold plate towards the electrode, or if you apply the voltage on the other side, we can pull it towards the other electrode. And that is used to counteract a small rotation that we have in the coil as the coil moves up and down. So the biggest challenge in this experience is also the part that is the most fun. And that is, you connect all the different disciplines in one point. So in the Kibble balance, you need to have mechanics, so it's a mechanical apparatus. You need optics, because you need to measure the position of the coil, and you need electrical measurements. And all these measurements are at the limit of what's possible.
We are starting with such a single crystal made of silicon, and we prepare a sphere, as you see here, from this crystal, and we determine the number of atoms in such a sphere by two different experiments. First, we are measuring the distance of the lattice planes of the atoms in the crystal to determine the volume of one atom, and then we measure the volume of such a sphere by measuring the diameter. And if we divide the volume of this sphere by the volume of one atom, we can determine the number of atoms in this sphere. So in principle, it would be quite easy to define the kilogram by a special number of atoms of silicon.
But there's one problem. There exists not only one type of silicon atoms, there are 3 isotopes with different masses. So we also have to determine the concentration of each isotope in this crystal, which is then in the molar mass.
This shows the inside of the interferometer. Here the sphere is placed between the objectives and the beam is coming from both sides, running into the interferometer, and we can distinguish between 2 setups. One with a sphere in a lifted position where we can measure the distance between the reference faces, and then the sphere is positioned so that it is in the center. And then we can measure the gaps between the surface of the reference phase and the surface of the sphere. And the difference of both measurements give us the diameter of the sphere.
Indeed, we had 3 big challenges to solve. The first one was already solved more than 50 years ago. It was the measurement of the atom distances in the crystal traceable to the meter.
Yeah, second challenge was the determination of the volume of the sphere. Therefore, PDB developed a special measurement device, the so-called spherical interferometer. And to get really proper results, it was as well necessary to manufacture a perfect sphere. And that took us more or less more than 1 decade. Today we have the roundest sphere in the world, and most probably as well in the universe.
The third big problem was the isotopical composition in these silicon spheres. It turned out that we are not able to determine the concentration of the isotopes in natural silicon accurately enough. Thus we had to switch to isotopically enriched silicon, silicon-28. And this is a very expensive process. That's why such a sphere made of silicon-28 is worth around €1 million.
So this balance works a bit like a motor and a dynamo, so you can either inject a current to produce a force or move the coil to measure voltage. And doing this, you can in fact relate the mass to the Planck constant. So now, with such an experiment, we have sort of an absolute balance, and we will have to redefine the mass unit in the world using different balances like this. And we have to put that in the network where we can compare different masses together and make the basis for the new kilogram.
I think it's really great that we have 2 methods that can be used to realize mass from a fixed value of the Planck constant, the sphere and the Kibble balance, because it's nice to have 2 methods. This way you not rely on any one method, and if there's a problem with one method, you still have the other one. And the point that both methods agree makes the system very strong scientifically.
The new concept consists of 3 steps: the definition, the realization, and the dissemination. The definition we talked about is the definition by Planck's constant. The realization ends with a physical body in a laboratory, either the weight piece that was calibrated in the Kibble balance or the Avogadro sphere that went through all the measurements of crystal structure and sphere volume. The dissemination now multiplies that information, extending to national measurement standards or industrial weight pieces and balances, so that finally every balance on Earth indicates kilograms and grams and milligrams related to Planck's constant. This is the M1 mass comparator, where the silicon sphere and stainless steel kilogram weights are compared to each other as part of the first step of the dissemination of the kilogram.
The idea behind this revision of the International System of Units was such that the end user will not find a bump. So it will be a continuous event. So the kilogram before and after will be the same. But the difference is, philosophically, it makes so much more sense. We don't have this artifact that's kept in a vault in Paris anymore, giving us the mass. We have now a fundamental constant of nature. And in a way, we finished that arc that was started at the French Revolution to make a measurement system for all times and for all people. Because the fundamental constants are really for all people. Everybody can access it with an instrument. And the fundamental constants, as the name implies, are constant, so they don't change. So we have now a system of measurements that's for all times and for all people. So philosophically, it's just beautiful.
On May 20th, 2019, the great change of the International System of Units comes into force. From that day onwards, all measurements are based on natural constants. This makes the SI fit for the challenges of the 21st century. So, what will happen to the international prototype of the kilogram?
In the first period of time, not much will happen. It will still be stored in the same way it has always been stored at the BIPM, locked up with access granted by the International Committee. Because it will start out with as a valuable standard, because even though its mass will no longer be defined as exactly 1 kilogram, its uncertainty will be small. 10 micrograms in a kilogram is a small uncertainty, so it still has value as a standard. And later on, say 10 years down the line, it could be checked to see if its mass has been gaining, increasing or decreasing with respect to an invariant definition, which we now have, because a lot of people have speculated it was doing one or the other, and we should be able to answer that in the course of time. So I think that, as I said, not a burning question, but it would be interesting to know, and I hope we find out. But just as a historical anecdote, really, not because we really need to know. And so this is how it works. It takes a long time to make big changes, and so yeah, there's, on top of the scientific stuff, there's also political and sociological and all these other questions, so that have to be resolved. You have to have most people on board before you can make the change.